In Dynamic Designer Motion, it's possible to export simulation data into a comma-separated value file, or a CSV file. It's also possible to import this data for your motion, and DDM will create a spline for interpolating between the data points for the simulation. And we're going to look at both of those now. Here is a little mechanism that has two revolute joints, and we're going to open this in the motion environment and create a simulation. So we need to make a new mechanism, and we'll just let it automatically ground, say which parts are ground and moving. And now we want to add motion to link 2. So we're going to let the physics engine perform our inverse kinematics for us. That is, we're going to have this part translate in, we're going to specify the motion in Cartesian space, and the simulator will determine the motion in joint space. Okay, so we're going to add motion on the part, and the motion is going to be relative to ground. We'll put it right here at the center of that circle, and the z-axis we want it to be, we'll point it up, so let me select that face of that cylinder, and select the x-axis. We'll choose this edge on that base part there, so that edge, which is parallel to the world x-axis. Okay, and the motion we're going to specify, translate in x, we're going to specify the velocity, constant velocity of, let's say, 125 millimeters per second. Okay, and go ahead and run this simulation. And that's pretty slow. I think I will increase that velocity just so we can see a little bit more what the displacement is. So in order to change things, you have to delete the results. And then let me go back to that motion and change the properties. Motion, we'll say 200 millimeters per second. Okay, and I'll change the view. We can look straight on the top. Alright, and run the simulation. And you can see it translating in the x direction. Well, it's not exactly translating the x direction, we see. So to see what it really did, we can go create a trace path, and the point is going to be, again, so the component will be this part, and then the point on it is going to be there. So we see it didn't trace a straight line like we kind of wanted it to. Instead, it did this. Well, the reason for that is whenever we specified the motion, we didn't fully specify it enough. Okay, so we need to delete those results. But anyway, I'll talk about why this is not just a translation in the x direction. So we delete these results so we can look at the properties of the motion. You can see motion, we specified translation in the x direction as a constant velocity, but then we also have translation in the y direction. So this is a planar mechanism. That part is free to move in the x and y plane. And we allowed the y translation to be free, so it's unconstrained. So that motion that was generated in the simulation was a translation that did have an x velocity of 200 millimeters per second, but the y velocity was whatever, sort of the path of least resistance. So in order to get motion just in the x direction, we're going to have to change this from free, and we'll say the velocity in the y direction is 0 millimeters per second. And now rerun the simulation, and it should move in just the x direction. Okay, so that looks like what we wanted. So there's our Cartesian motion in the x direction, and you can see the trace path that we had. Alright, and now we're going to use this simulation to figure out what joint torques are necessary for that motion. So typically when we find joint torques, we add a motion to the joint, and then you can find the motion generator force, or torque in this case. But since the motion that we applied was on this link, we don't have any generating torque on the joints. So we're going to export the joint positions, create a new simulation, and use those as our position or our motion. A lot of words, and hopefully it'll become clear with these steps that I'm about to take. So we have our joints. This revolute joint is right here, and we want to plot the the projection angle about the z-axis. So there's the displacement of that joint, and we'll do the same thing for the second revolute joint, projection angle about the z-axis. Okay, and now right click in the unshaded part, export to CSV, and just overwrite that, and do the same thing for joint 1, export CSV. Okay, so now in order to illustrate what I was talking about importing that data, let me create a new mechanism so we can have the same motion model but several different simulations with the same assembly. Okay, we have these parts grounded and moving, and you can see that that motion is no longer gone, so there's no simulation to be run. So we're going to add motion to the joints now. So we've got this revolute joint 1, and properties. We're going to add motion, rotation about the z direction, and this will be displacement. And instead of being a constant displacement, we're going to use a spline function. Now, in the Dynamic Designer Motion manual, it talks about the differences between these two spline methods, and this one is more accurate, so we'll go ahead and choose that one. And we're going to load the CSV file that was exported from our other simulation. And so that was the joint positions every 50th of a second. So there is that data, and we want to go ahead and hit the check mark, so it'll create the spline. And now we have the motion of that joint, and we'll do the same thing for joint 2. So we want a motion about the z direction, displacement, and we're going to have a spline function. So we're going to load this data. So this data is the position of the joint 50 times per second. But so that's 0.02 seconds, or 20 milliseconds between data points. So you can see it here. At every 20 milliseconds, there's a new data point, a new position value for this joint. And the simulation will likely run at a smaller time step than that. And so this spline creates all the data points in between the values that we're loading. Okay, so now we have our motion on the two joints, and go ahead and run the simulation. And create a trace path again, just to see. Alright, look at it straight from the top so that we have a good perspective. And you can see that we ended up with that same translation in the x direction that we had from the other simulation. And now we can plot the rotary motion generator moment in the z direction. So this is the moment in the world z direction. And now we see that for joint 1 we require up to 406 Newton millimeters, and for joint 2 43 Newton millimeters in order to get the motion prescribed.